Thank you. Good morning, everyone. So today our topic is on rise of geospatial intelligence in engineering construction. So this is our team, as you actually introduced. We are from a digital team from L&D construction, headed by Dr. Rajesh Kumar. So we have various experts in our team from JS to water management, um, um, construction management, and BIM engineers. So and in development sector. So all this we have a variety of experts in our team. So our main goal of our team is to develop digital engineering and operations in construction sectors. So I'm going to explain about the geospatial activities which we are currently doing in our water projects. So this is the basic of geospatial technologies. So geospatial technologies involves basically of four components: remote sensing, GNSS, GIS, and scanning. So remote sensing is a technique by which we can able to collect data without any physical contact. So this is the basic schematic drawing of remote sensing, by which we could able to collect data with the satellite without any physical contact. So this is a simple schematic from by which we will be capturing our satellite imageries, which you see in Google Maps and in mobile maps, and also how the satellite is capturing this imagery, and that data is then processed and will be exported as images and published to web as a web services. So this GNSS is nothing but GPS, which we conventionally say. As earlier, it was only with the GPS technology. Now all the countries have their separate navigation satellite systems, which collectively we called as GNSS. So the primary aim of this GNSS system is to locate one position, but in the advanced methodologies, we are using this technology for surveying purpose to collect accurate measurements of X, Y, and Z coordinates of any point in our Earth, and also to measure between 2 points. We are using DGPS technologies mm, to measure accurate distance between 2 points and elevation between 2 points. So this is JS. JS is software systems where we use these geographical data for processing, viewing, and doing any analysis to get our desired results. So these are some of the geospatial applications which we use in the water industries, like hydrological analysis, site suitability analysis, groundwater analysis, 3D analysis like contouring, preparation of DEM to visualize the terrain in 3D, and progress monitoring, location-based progress monitoring, web-based progress monitoring, real-time progress monitoring through drones, and LiDAR survey to collect the terrain data, GPS survey to collect the exact X, Y, Z of one particular point, and consumer survey for our urban planning, urban water planning kind of thing, and drone-based surveys, nothing but taking imageries and elevation details of the terrain. And in O&M, we are using the GS data for leak detection, spatial query, demand allocation, and reducing the non-revenue waters and data management. So, as GS is capable to handle high capacity data, it is easy to store the data with high volume, in TBs in a cloud-based systems in a in GS platform than any other data types. So these are some of the technological trends which we use with our geospatial technologies for our internal applications, like LiDAR survey for precision surveying, artificial intelligence for chuck planning, 3D and digital twins for progress monitoring and JSBM integration, drone technology for surveying and progress monitoring, automation of pipe routing, layouts, chuck planning, cloud for data management like ACC, WebGIS, GeoBIM, artificial intelligence and virtual reality for project reviews. So these are some of the digital solutions which we are following for our irrigation projects particularly. Chuck planning, automated chuck planning, contour generation from satellite DEM, automated pipeline routing for irrigation projects, storage capacity estimations for dams, GSBM integration, excavation quantity estimations for pump houses and water intake structures, filter analysis, LIDAR survey for all of our projects, watershed and stream generations for hydrological analysis, feature extractions using deep learning technologies for our urban analysis, and dashboards for progress monitoring and access management. These are some of the GIS solutions which we are providing for all our projects. So let me explain the what actually in our department we are mainly focusing on lift irrigation systems. So this is a typical drawing of lift irrigation systems that we follow in India. Here you could able to see water is pumped from an intake well or existing reservoir structures through a pump hose, and then that is transferred to a delivery chambers. Uh, Delivery chamber, from delivery chamber it will be transferred to a distribution main, and from distribution main the water is transferred to each OMS outlet management system. From outlet management system, it will transfer to respective chucks. Chucks means it's a combination of land parcels of the farmers. So each chuck will be defined. So the project will be defined like how much water, how much discharge should be given for each chuck. So this is how the project will be planned throughout the command area. For each outlet, for each OMS, there will be some 10 outlets or 6 outlets depending upon the project specifications. Using this OMS, we will control the outlets, and the water will flow to the farmers field finally. So this is a typical drawing of irrigation systems. So this process I'm going to explain one by one how we are automating this process using JAS. So this is the timeline which we will take for this complete pipeline design process. For surveying and data collection, it will take 15% of time, and for chuck planning purpose, it will take a 40% of time, and pipe routing it will take 20% of time, and to do the hydraulics and L section designs, it will take 15% of time, and to prepare the final layouts for approval purpose, it will take 10% of time. This is a typical timeline which we will take, and we have automated this process or increase the efficiency of this process using the geospatial technologies. Like conventionally they use surveys using total stations, GPSs, to collect the informations for actually as our projects of our wider area like 2000, 3000 square kilometers. To taking the survey itself, it will take some 1 year to 2 year for mega projects. So using data survey technology, we could able to complete these surveys with the deliverables in 6 months of span. But for small projects, we can able to complete within a span of 1 month to 2 months also. So this drastically reduced the project timeline almost 20-25 percentages. So for the past 5 years, we are mandating data survey for all of our irrigation projects. Next is chuck planning. Chuck planning is a process by which we will cluster the land parcels of farmers for a specified area. Like as per the tender specifications, usually it will be 2.5 hectare or one hectare chuck. So we will cluster the lands of one hectare of one hectare. We will cluster the farmers land, and we will combine. And 21 hectare as a 21 hectare subcheck as a single check. So for each check, we will place one OMS. So this planning will take about 40% of time. So for a project of 200 square kilometer of land, it will take about 1.5 years to 2 years of the time for the for this truck planning purpose also. It will take sometimes more than 2 years, 2 years also for a very large projects with complicated terrains. So by automating this process using JAS, we could able to reduce this time drastically to 2 years to we can able to complete almost in 6 months of time. So one fourth of time we could able to reduce if we have all the data in JS formats, and government also pushing all these revenue records all these topographical records are in JS formats in the recent years. So using the JS automation clustering using machine learning technology, we could able to do this process. And pipe routing also, we are using the least cost path method to automatically generate the pipeline routings, which could able to reduce 90% of time, manpowers which you are using in pipeline routings, and which could able to also save the 15% of the total pipe cost, because as this is a cross country routing pipeline design, so there is no proper corridors for the pipeline routing, so you can able to lay the pipeline throughout the command area. So based on the conditions which we are giving, we could able to customize these things. All this process I will be explaining in the further slides with details also, how we are doing this. And automated layer generation using JS is also reduced 90% of drafting times, because to draft each layout is a very time consuming process, as manually we need to put the layouts, all these title blocks, and to annotate the each features. It will take a lot of time. By using the map series technology in JS, we could able to automate these process, as all the design data we are exporting to JS in with all the attributes within it. We could able to automate this process based on attribute driven map series technology. So this is the aerial survey. This is how you will be getting the output of aerial survey. You could able to see the exact 3D model of the terrain here. So you can able to see all the transmission tower, transmission line, trees, the terrain details with all elevation details within it. So we will by post processing technologies in the lidar survey, will remove these external factors, and will we will develop one DEM which have the digital terrain model, which will be having the elevations of only the terrain details, which should be used for our engineering purpose. And all these surface model also will be used for some intervisibility analysis for OMS. As OMS have the radar communication system, we need intervisibility between two OMS to communicate with each other, so that we can able to assign which outlet system can be opened at a time. So this lidar have the accuracy of 0.5 to 10 relative to its sensor, and also vertically for mapping we will be having a centimeter level accuracy. So you will be having each data like in centimeter level accuracy, xy and z, so which is very high accurate data for any engineering planning, and also for quantity estimations. And you could able to plan it efficiently for the hydrological design, because a small slope in a pipe will also affect the cost drastically. So if we're having this much accurate terrain data, we could able to precisely do the design calculations for hydrological analysis of the pipelines. So these are the derivatives of lidar survey. So this is what a DEM, and we will be getting ortho imagery and lidar point cloud. So DEM will be having the elevation details of each and every 1 meter, 1 meter by 1 meter grid will be having elevation details. And ortho imagery will be having exact high resolution imageries throughout the command area. And lidar point cloud will be having a 3D representation of that area. This is automated check plan which we'll do. So this is how the one check is defined. So you could able to see here. So these are the plot numbers of individual farmers. So we will be combining these plots as one subcheck. So these each color represents, so this dotted line represents a subcheck, and each color represents a 2 hectare check. So between which we will be placing one outlet point, and collectively 20 subcheck we will call this as a check. This is how we will be dividing each and every farmer's land as a check, and we will be placing OMS for each check throughout the command area. So in case for a mega irrigation project, we will be having around some 5,000 to 6,000 chucks like this we will use to prepare, so which will take a huge time when we are doing manually, because it need to be calculated for each area, and manually one need to cluster these uh, maps. But using the genetic algorithm and machine learning technology, we automated this process using the arcpy modeler with the Python scripting. We have automated this process based on the attributes in the revenue records to combine based on that, based on the area as per the revenue record. We are combining this for 1 hectare, and then we are combining as a 2 hectare, and then those are all combined as the 20 hectare checks. So this is how we will this will raw revenue records, and we will segregate which are all the cultivable land and non-cultivable land. So for our chuck mining purpose, we will be considering only cultivable lands, removing all the non-cultivable lands. So this hatched area is non-cultivable lands. So only the cultivable land is taken for this process. All this process is automated using the Python coding. And then automated outlet and OMS extraction. So after preparing this chuck, we need to place outlet for each chuck. So that those outlets should be as the highest elevation point of each chuck, so that if the outlet is placed at that point, everybody can able to get the water throughout the chuck. That is the main idea. That's why we are placing at highest elevation point of each chuck. So as the water flow from higher elevation to lower elevations, so we will be having outlets at a higher position, and our outlet control system at a centrally placed for this outlet, so that the pressure, it won't affect the pressure of the water flow. That this is also before this, when you are placing manually with the contours, one person need to place each outlet manually based on his perception, based on the contour drawings, using the older survey details and all. But by taking the advantage of these DEMs from LIDAR survey, we can able to automate this process as it accurately place these outlets at each chucks, and accurately place this outlet control system also at centrally to these points, based on the spatial spatial analysis. And these and all we will be calculating through the zonal statistics technology in JAS. And then this is a micro distribution network systems. So once this outlet and OCS is placed, we need to connect this outlet based on this OCS systems. So actually, I am explaining this based on single check, but there will be a 5,000 to 6,000 checks for each project. So joining this joining this line itself, it will take a lot of time when you do it manually. So based on this IDs of OCS and subject IDs, we are automating this process again with Arc payments. It is a Python systems which you are using in ArcGIS platform, ArcPy coding to connect these lines automatically. So this is automated distribution network. So as I already said, this as irrigation cross country based pipeline systems, we don't have any corridor by which we need to lay the pipe. You can able to lay the pipe anywhere, but with some conditions. It should avoid minimum forest land, it should not avoid the water body, it should have minimal highway and railway crossings, it should not cross the streams multiple times. So we have this kind of restriction in this process. So what we try to do is, we have mapped what are all the restrictions we have as a land use land cover map and slope map, ridge lines, roadways and rail lines, streams. So we have converted these polygons into a raster format, and we have assigned weightage for each land use classifications, slopes, ridge lines, railway lines. Like for example, if you like if your route doesn't need to pass through this water body or forest lands, we will be giving giving them as a high cost. Like it is like the cost is higher for that kind of land uses, and lower for agricultural barren lands. And wherever we need doesn't need to cross, we will remove that land use from that raster itself, so that it won't cross through that thing. And roadway lines, railway lines also we will be giving higher weightage, so that you should have a minimum crossings, minimum number of crossings through the railway and roadway lines. So these kind of weightages we will fix, and using this least cost path analysis, we will generate the routing throughout our command area multiple times for our best for best route, which also pass through our hydrological design. So once this routing is done, we will do an hydrological analysis by assigning the diameters. So it will have some multiple iterations. We will assign the diameter, and it should match both our hydrological design, and also it should be minimal length also. So like this we will do multiple iteration, and we will fix our routings. As earlier, when you're doing it manually, manual perception will be only it will be there. We can able to route the pipe anywhere as we like, and then it will be using multiple iteration will correct this line. Even after finalizing the pipeline routing also, we couldn't be sure that is the minimum length by which we could able to achieve this comment area. But using this least cost path analysis, we could able to reduce this length drastically to 10 to 15 percentage for many projects. We are using these things, which is reducing 10 to 15 percentage when we are doing it manually, and we are doing it with the automated process. So which will be a huge gain for uh, a huge gain we are saving in the pipeline. So which is our most cost consuming thing in all of our projects, because lift irrigation is mostly some 80 to 90 percentage of cost is based on our pipelines only. As we need to lay the pipelines near to 2000 to 3000 kilometers of pipelines, and the diameter of pipeline will start from around 3.5 meter in the sense it will be a size of a room. So those kind of pipeline, it is very costly, and saving some few kilometers of this pipeline will also result in a huge savings to almost 50 to 60 crores in each projects. This is one of a kind which is done first in the world, as no one ever tried for a distribution least cost path method for a distribution network. There are a lot of least cost analysis which are done for a linear pipeline, like only one single route. uh, People have done a lot of researches, and they are using it for a distribution network. We are the first to do this, and this has been widely accepted and published in many international conferences. We are published in pipeline technology conferences in Berlin, and we also showcased this in a Singapore Water Week, and now we are going to showcase this in Australian Smart Water Utilities Conference, which is going to happen next week probably. So this is how the GS layout looks out. So people, you may if you have seen the CAD layout, which will be in very common color, black and white colors mostly. So it will be very difficult to understand the CAD layout when you are placing lot of informations in a layout. That's why we have used JS layout for this command area, because as we are placing in many number of informations here, like ROR, revenue records, check, subcheck, OMS, pipeline routing, and notes of these pipelines, and all these annotations. So this is very difficult to understand in a CAD layout. That's why we have tried with the JS layout, and successfully accepted by all our clients, as as GS layouts could able to give the clear idea of what is available in the layout, and with the different colors and different stylings, we could able to differentiate the each and every parameters in a layout in JS, much effective than the AutoCAD drawings. And also the main advantages is we could able to automate this process, as automatically all these automatically it will generate many series of layouts in a single click. And for these kind of layouts, to placing a table for each layouts itself will take a lot of time in an AutoCAD. But in JS, when you're automating, it will automatically creates the tables depending upon elements we are uh, uh, what elements we are placing in that layout automatically. As like, this is one check. If it is if by automating, if you are automating some 2000 checks, so if it go for another check, these tables are automatically updated based on the pipelines details available for that check. So this level of automations can be done in this JS platform, which is very effective, and we don't waste any manpower just for drafting purpose for the submissions. So this entire process has reduced our project timeline effectively off of our time. So the projects which took some 1 year for engineering purpose, now we are doing it in 6 months of time, and which took some 3 years of engineering time, which we are doing in 1.5 years now. So in the last 5 years, we have achieved this kind of digitalization in engineering, which is drastically reducing the manpowers, and also the use of engineering manpower just for drafting and planning purposes. They can focus more on hydraulic designs on engineering perspective than for this kind of drafting and planning purposes. So this is another another applications which we are using for our projects. So many of our projects will be having a dam constructions within our scope. So for it is for dam construction to estimate the storage and how much bund is required, uh, what is the height of bund required, how much cutting and filling required for this bund construction, and to have a required capacity. These kind of analysis we are fully automating through JS platforms, so that we could able to get that what to say minimal cutting and filling quantity. We could able to achieve the required volume. So these optimizations we are doing with JAS, and we are using for our dam construction projects in this. And also we could able to visualize in 3D for the we will model the dams with all the terrains and imageries. We could able to visualize in 3D, and that is showed to our clients, and also for ministries also, so that they could able to easily visualize what is going to happen after the project, and how much bund it is required, how much height, what will the height of the bund. So in some cases, for the we are doing a thin bund of nearly 30 meters also, which is a very huge. And the bund cost itself, it will go to some 200 to 300 crores for this kind of earthen bund structures. So these justification can be better suggested with the JAS models than just drawings which you are creating with AutoCAD. So these are some of the workflow automations which we can do in JS, like automations. So for our tendering purpose, we don't have been having the survey records. So in those cases, we use the satellite DEM to generate the contours for initial tendering purpose, and watershed and stream analysis is for to understand how much water will be discharged at this place. And this will be explained by Guganesh in detailed in next session for all this hydrological analysis and all. And this is another excavation estimation in JS, like how seen for all our pump houses and intake structures, we need to do huge excavations, which should cost around some 50 to 60 crores sometimes. Say as you can able to see in this imagery, the top is around 363 MSL, and the bottom is around 325. So almost 40 meter of excavation is required for this kind of constructions. So which will be costing around some 50 to 60 crores in these cases. So yeah, precisely estimating these kind of estimation will could able to save us a lot, and also we can save us a lot, and also we could be having an better agreement with our subcontractors who are doing the construction, who are doing this excavations. So these models we can able to create and estimate in JS in much in much shorter span of time. Like we can be able to do in 4 hours or time, we can model and we can able to calculate the excavations. Manually, if you are doing this, and also manually if you're doing it, will take some 2 3 days of time, and also that won't be a precise as we are calculating with JS. And these are the this is the digital geography. So as all our data we are now we are doing in an digital platform. The output of all this data also, it will be in a digital platform, and like a digital platform in the sense, before under only layout, people will execute their their project with the help of hard copy layouts. But now we, as we are doing engineering and designs with softwares, these are exported to JS database, and this JS data is published to online. And on the site engineers and site people can able to execute any this pipeline projects based on the digital data from their mobile or laptop. So all this data, including as you see, as I showed in the layouts, this data is in digital platform which is published in a web portal. If so a person need to if a person need to execute a pipeline from this place, if he stand it and if he goes to if we go to his place, like how you check in Google Maps, if we go, it will show what pipe need to be laid there, and how what is the length of the pipe, and all the details of the pipes. They can be able to see, and what diameter of the pipe, what material of the pipe need to be laid, and what are all the ROR regions, like who are all the owner of the farmers of the particular lands. Those details, everything will be people able to people able to see, to get the permissions of them, to get uh, like to get approval village wise. If you want to lay the pipelines, they need to get there are a lot of permissions required. If it is crossing through the forest area, you should get approval from the forest authorities. And if it's pausing through any government lands, you should get the approval from the concerned authorities. And if it is going to private lands, they should get approval from the village administrative officers, and with approval of all these farmers. For all kind of all this kind all clearance like this, people can use this. People are using this kind of digital geography web applications, um, for easier calculations and easier execution of the project. So this is the progress monitoring. So earlier, people used to note that this much amount of pipelines has been laid, this much excavation are made, this much pipelines are hydro tested, like that. Only this numbers will be noted. But for this kind of pipeline projects, that is the mega pipeline project, which covers a huge area, like covering some 200 300 villages and all. Only with these numbers, people cannot able to understand where the pipes are laid, if any gaps are there, where the pipes are left. Geographically, people couldn't able to understand how much project is completed, and how much which dia of pipe is completed, which dia is not completed. Like this, there are a lot of uncertainty happens. So that's why we have created these JS based dashboards, where people can update the progress with respect to its geographic location itself, based on the IDs, pipe IDs, that we have assigned to each pipelines. So once we are tracking the progress like this, people have an exact idea on the of the projects. So how, where the pipes are laid, where the pipes need to be laid, how much hydro testings are done, and for this village, how much pipeline needs to be laid. So all kind of information they can able to extract from this progress monitoring dashboards. And the progress monitoring is can be captured within like within using the mobile application itself, based on their location. So once the pipeline is laid, the site engineer from his place itself, he can able to select the pipe, and he can enter the applications, sorry, attributes related to that pipeline, like uh, mostly these are all pre-filled based on the design data. So the site engineer will be filling, so when the pipelines is laid, the data of laying, and who is the subcontractor, and any remarks if you need to add it, he can add, and any documents you need to attach with respect to that construction, they can able to attach, and the photographs of this, once it is completed, he will be taking a photos, and it will be uploaded. That will be these collections directly uploaded in a web interface, using JS cloud, which we are using is ArcGIS Online. It is a cloud-based JS platform. So in real time, you could able to capture the progress, and also you could able to visualize all these images and attachments related to that construction activities. Once the site engine is upload, anybody from office, like a business heads, they can able to view these progresses, and also what's happening in the sites with respect to the images which they're capturing. So all these things will happens uh, real time, as everything is connected through a cloud platform. This is as-built update through mobile applications. It is similar to progress monitoring. See, actually, during the execution of stage, there will be some deviations in the pipeline alignment based on the site conditions. So those details need to be captured as-built. As any deviations are there from the design pipeline, people used to capture that deviations of the pipelines, and they will be updated as built through the same mobile applications which I showed earlier. So this is one process we are using for our urban planning. So for any urban planning, urban water infrastructure planning, um, the first step is to take the consumer survey. For consumer survey, we need to understand how much buildings are there in the city. So for that, people used to manually digitize the building footprints, but recent developments in deep learning, we could able to extract the building footprints based on satellite imagery, or our survey imagery. As I showed, for a doing the AI survey, will capture the imagery also. Based on that imagery, with deep learning technology, we could able to extract the building footprints, and person manually goes and take the information about each building. So how much persons are living in that. So what should be the demand required for each building, and based on that, automatically will create a zone called as DMA for urban water planning, and we will be providing water supply to them. For this process, we are using deep learning technologies for to extract the building footprints automatically. And also, this is also another deep learning tools for image segmentations. As I earlier said, we need a exact land use land cover for this automated pipeline routing. So based
அவ்வளோதானே.
So based on the imagery, we could able to automatically do the image segmentations. So as you see here, I could able to classify the settlements separately, forest regions separately, streams and water bodies separately, and what are the cultivable and not cultivable regions. We could able to segregate here. This is then fed into for this least cost path method by giving the weightage to it, and we will process the automated pipeline designs. And these segmentation is also used for many applications, as for getting forest clearance, to understand how much cultivable areas land in the command area, how much water body is available in this command area. You could able to estimate those also in this. And this is a topo sheet dashboard which we have prepared internally. This dashboard, we have used Power Automate technology from Microsoft. So we have integrated the Power Automate and ArcGIS online platform. We are storing we are stored topo sheets in a SharePoint. SharePoint is a Microsoft cloud platform, and those unknown form is attached using the Microsoft form, and this is linked with the JS platform. So people who need a topo sheet of the one particular regions, they can view and they can view the status of the availability of the topo sheet, and they can fill this request form. Once they are filled, uh, the Power Automate this process will run in Power Automate. It will search for the required topo sheet in the SharePoint, and it will take that topo sheet and it will attach to a mail. It will automatically send mails to the person who is requesting to it. So this we have set up this dashboard that will be working within our LNT domain. So person with the LNT domain email, they can easily request here, and they can able to get the topo sheets automatically without any person's interventions. So these kind of automations we are doing for many kind of this for providing data. So recently we have developed one like one web portal for this contour and watershed also. Sorry, contour and this chuck planning for tendering purpose, so that people without like without depending on another people, when they need any contour for the region, they can just go to the portal, and they can give their required area where they require the contour. And once they uploaded those data, the system will automatically go to the server, and based on the data which we are like a DM data which is stored in the server, it will run the process and will create a contour, and it will just throw it will give a download link to that persons, and they can easily able to download the contour of that area. And similarly they can do for this chuck planning. So once they are given the area, it will automatically calculate how much cultivable and non-cultivable regions are there in that region, and they can give the uh, desired chuck area they are required, and it will automatically do the chuck planning, and it will give the download link to the persons. So these kind of automations we are doing within our team, so that people will not depend on another person's availability to get the certain data which they are required. So this is how we are automating the engineering within our IC and SPG, so that people without what is the main aim is that people should not depend on another persons to get the desired, because everyone availability will be different. um, so persons when they require some process need to be done automated. So like this we are automating all the processes, all the engineering processes, so which also reduce the manpowers drastically, and also the work will be done on time without depending on the other persons. So these are some of the process improvements we could able to achieve. We could able to achieve using the GIS in last 5 years of time. So here I can able to explain. So the check planning process, before it was done using AutoCAD and Excel. The manually they will add each area, and they will draw one chuck in AutoCAD. So for each chuck, it will take a lot of time in AutoCAD that I said that for a mega lift irrigation project, it will take some 3 years. So actually, recently we have two mega lift irrigation projects of around some 5,500 square kilometers, which should conventionally take if you want to do check planning for these two projects, it will take some 5 years if the one team, and almost 2 to 2.5 years with two teams. But we are done in within 1 year of time period with a single team using this GS tool sets. And also for pipe routing, earlier they used to do in AutoCAD and Google Earth. They will create a KML, and then they will convert into CAD, and then they will upload into WaterGem platform, and then they will be doing the hydraulics. But nowadays we are doing with ArcGIS, and which is directly imported to WaterGem platform with all elevation details and elevation details within it. So which have high compatibility with the WaterGem than the previous data sets. So which can which will end up in doing this process much effectively, which could able to save 90% of man hours in this process. And roll stations, we had earlier it was with roll stations, sorry, survey. Earlier it is with toll station and GPS. Now we are mandating all the projects with the lidar service, with drone or aerial lidar survey. On flood risk analysis, we are doing with HMS softwares and completely in-house, which will be explained in next sessions by Mr. Ronesh. And cut and fill and storage estimations, earlier it was done with Civil 3D or in Excel manually. Now we are doing with ArcGIS, and we have done one methodology in JAS by which we are doing these processes for all our dam constructions and intake and pump house excavations. And progress monitoring, earlier it was done with Excels and any other softwares. That too, it won't be having any geographical locations within it. For the pipeline progress monitoring, now we are doing with ArcGIS online. And layouts, earlier it was with the AutoCAD, and now we are doing with ArcGIS software itself. So here we are unifiedly using a single platform for all our mechanical design processes, so data interoperability and conversion of data between different softwares. These times also reduced greatly, and the data interoperability, loss of data between when the construction is happening is also, sorry, when the conversion is happening is also reduced. So thank you. This is how, from this I will end my sessions on geospatial technologies, which we are using for our AAA projects. The next section will be given by Mr.